In this example, we want to check to see which of the following reactions cannot occur. That is, which reactions violate some conservation law. So let's check each one of these reactions individually. So starting with the first one, where we have a proton plus an antiproton, the little bar means antiparticle, goes to a neutron plus a photon. So first let's check out the charge. So if we check to see if charge is conserved, a proton has +1 fundamental unit of charge, an antiproton has -1 fundamental unit of charge. That goes to a neutron which has no charge, and a photon which also has no charge. So that checks out. There's a sum of zero charge over here, a sum of zero charge over on the other side. Next, let's take a look at strangeness. So if we take a look at strangeness, and we can refer to the table on the previous slide, we can see that a proton and an antiproton, those are both not strange particles. So the proton and the antiproton, and remember when we are looking at an antiproton, we basically want to take a look at the proton numbers and then just take the negative of them. So for strangeness, the proton and the antiproton both have a strangeness of 0. They are not strange particles. And that goes to a neutron. A neutron is also not strange. And photons have 0 for everything. All of the conservation numbers are 0 for a photon. So even though a photon does not appear in this table, you can just remember that a photon has 0 conservation number for all the different kinds of conservation numbers. So strangeness is conserved because there's just no strange particles here. And then we should also check, let's see, lepton number. Well, we don't have any leptons. We have a proton, an antiproton, a neutron, and these are all baryons. They're all different kinds of hadrons. They're not leptons at all. And then a photon is 0 for everything. So we don't have to worry about checking any lepton numbers. But we should check baryon number because these are baryons. And so a proton has a baryon number of +1. We can see it is in the table right here. So the proton has a baryon number of +1. And an antiproton, you take the reverse of whatever the conservation number is for the proton. So that would be -1. That goes to a neutron, also has a baryon number of +1. And then photon 0 for everything. So we can see that over here we have a sum of baryon numbers of 0. Here it's +1. So this is in fact violated. So this proposed particle reaction violates conservation of baryon number. So we would say that that one is no good. So let's next check this second reaction. So once again, we want to first, let's give a charge a check. And a proton has +1 fundamental unit of charge. This is a pi-. The minus indicates that it has -1 fundamental unit of charge. That goes to a neutron, which of course is electrically neutral. And we have a pi-0, and a pi-0, the 0 indicates no charge. So it looks like that the charge balances. That's not a problem. Now, so let's next check, we could check strangeness. And if we look at strangeness for all of these, none of them are strange. We have some mesons, and the pi-0 and the pi-, they're mesons. Mesons never have strangeness, so it's pretty much 0 for everything. So strangeness is not violated. Then we can also check, let's see, leptons. These are both hadrons, and these are also hadrons. We have no leptons, no electrons, mu's, tau's, or neutrinos, so we don't have to worry about any of the lepton numbers. And then we should also check baryon number. So the proton has a +1 for its baryon number. And since the pi is a meson, it has a 0 baryon number. So that's +0. That goes to a neutron, has a +1 baryon number. And then this is a meson, so it has 0. And we can check in the table, see that both pi's, yes, have 0 baryon number. And so that seems to check out as well. So it seems that this reaction is okay. It does not violate any of our conservation laws. So next we'll check out this interaction here. And we notice that we have a couple of different leptons. But first let's once again check out charge. So the has the muon has a -1 fundamental unit of charge, and the electron does too. And then we have neutrons, or neutrinos, little neutral ones. So those both have 0 for the charge. So it looks like charge is okay. But I notice I have a couple of different kinds of leptons here. So I'll need to check out mu lepton number. And for the mu lepton number, a muon has +1 for its mu lepton number. And so if we go in the table here, we can see that is the case. Here's the mu, and it has a mu lepton number of +1. And then that's going to go to an electron, which has a 0 mu lepton number, and an anti-electron neutrino, also 0 for its mu lepton number, plus this is a mu neutrino, and that has a +1 for its mu lepton number. So we have +1 going to +1, that checks out. And then we should also check out electron lepton number, since we have some electrons and electron neutrinos. So this has, the muon has 0 electron lepton number. And that goes to the electron, which has +1 electron lepton number, and an anti-electron neutrino. And the electron neutrino is here. You can see that this is the electron neutrino row. It has +1, and so we take negative of that for the antiparticle. So this would be -1 for the electron lepton number. And then we have mu neutrino, which has 0 for the electron lepton number. So we have 0 on this side, +1, -1, so that sums to 0 on this side. So that checks out as well. So then there's also baryon number and strangeness, but none of these are all leptons. So none of these are baryons, so they're going to have 0 baryon number. And since they're all leptons, they're also going to have 0 strangeness. So those two will also be conserved. So it looks like this reaction also checks out. So then we're left with this final reaction to give a check to. So first let's look at charge. So if we look at charge, this is a pi-, so it has -1 fundamental unit of charge. That goes to a muon, which is -1 fundamental unit of charge. And then we have a mu neutrino, which has no charge. So that checks out. And then we should check, well, we have a mu, so we should check the mu lepton number. This is a pi, so it has 0 mu lepton number. The muon has a +1, and the mu neutrino also has a +1 mu lepton number. So that does not appear to be conserved. In order for this equation to conserve mu lepton number, this would have to be an anti-mu neutrino instead of a mu neutrino. So it looks like that one also will not work. And we don't have to worry about strangeness with this reaction or baryon number, since this is a meson, not a baryon, and these are leptons. So that looks like that is the rule that is violated, so that would be an X for that one. So it looks like there are 2 reactions that are forbidden by conservation laws, and that would be the first and the last. So let's next consider this question. When an electron and a positron meet at low speed in empty space, they annihilate each other to produce 2 0.511 MeV gamma rays. What law would be violated if they produced just one gamma ray with an energy of 1.02 mega electron volts?